Okay, Assalamualaikum and good morning, everyone. So today we continue our lectures, and I think we have gone to a different chapter on Maxwell's distribution. So let me just already share the screen. So let me go to the whiteboard. So this is essentially what we are trying to do at the moment. So we are considering the case of particle in a box, sort of representing gas particles, and then the aim is really to go to the point where we can actually prove the Maxwell's distribution of for gas particles. So, and the sort of the initial point where we start is to look at this particular state. I hope this works. So, okay, maybe it doesn't really work as the way I wanted. Okay, so this is the essentially the quantum state of a particle in a box. So now, really, we are not supposed to consider quantum states at the moment. We really want to describe classical gas particles. So, but there's a difficulty with as I think I've mentioned in some lectures before, that gives us problem with respect to classical particles is that you have continuous variables. So now with that continuous variable, then the kind of calculation that you're going to do is going to be cumbersome because essentially involve integral. So what we're going to do is to start off with a quantum case. Okay, so this is the quantum case, and then we proceed to use a discrete. The quantum case will have your wave vector, which I introduced before. So the wave vector essentially is this quantity over here. Okay, so this is the x component of wave vector, y component of wave vector here, and then a z component here. Okay, so this really relates to if you have done quantum mechanics before this really relates to the idea of momentum, because the momentum is just simply your Planck constant times the wave vector. Okay, so in other words, your so-called k-space that is mentioned in the book is really your momentum space. Okay, so it's equivalent to each other. Okay, so and then how do you discretize it? I already mentioned that we're going to use some unit cell, and the smallest unit cell is when you consider this is a bit counterintuitive. In a sense, what's the largest kind of wave that can fit a particular length? So the largest wave that can fit a particular length is essentially given by n equals to 1. So basically you have what you call this is half wavelength. Okay, so this is half wavelength, and the largest that you can get, and then you cannot make it smaller, because then it will not correspond to a standing wave. Okay, because you need to obey certain conditions at the boundary. Okay, so in other words, this will be the unit cell. Okay, Okay, and this unit cell is given by this particular volume, or if you invert that unit cell, okay, then basically you get your density of points in your K space. So one of the things that essentially going to be useful for us is to convert. Okay, remember that these are essentially three-dimensional space. Okay, so one of the things that we already known in ordinary maths method, for example, if you have your vector x, y, z, okay, this is the Cartesian coordinates. You can convert this to a different coordinate system, which is your we call it spherical polar. Okay. So what we're going to do, we're going to apply this to your K space. Okay, so let me push this thing up. So when you apply to the K space, so apply spherical polar, polar coordinates. I have to be careful with to K space. So and then we're going to replace your replace kx, ky, kz, which is just like your x, y, z over here, by the spherical polar coordinate. I think I have some notes down here. Okay, maybe I should get rid of this. To make sure I don't move too fast, because they will be lagging due to the computer here. Right, I think that will be enough at the moment. Okay, so what we're going to do is essentially to write down your analog of your spherical polar. So your radius is now given by the magnitude of k, which is given by your kx squared plus ky squared plus kz squared. Okay, and then your theta, if you remember, this was supposed to be the angle between the z-axis with the vector, so this will be inverse cos of kz, component of the wave vector along the z direction, divided by your magnitude of your wave vector. Let me see if I can delete that. I don't have to do too much. Get these things. Bring this thing down back here. So okay, so your phi, and this will be the arctan of ky over kz. Okay. This is just very similar to the case of the ordinary position space. So what do we do in this particular case? Then we can now, one of the things that we want to do is to replace your volume element. So this is volume element in K space. With the new spherical polar coordinate. Okay, so let me just write in full over here. So this will be the volume element in K space using polar coordinates. So this is just like your volume element in position space. So you have K squared sine theta dk d theta and d phi. Okay, so now essentially what we're going to do, okay, before that, let us remember we need to consider the differential, because the volume of the case doesn't tell you about the states. So essentially we need the differential of the number of single particle states. Oh dear. Oops. Okay, see, I hope it doesn't disappear again. Number of single particle states. Okay, so that is the one that which has, now why we started off with this was to refer back to this single particle states. Okay, over here. So, and they are labeled by this kx, ky, kz. Okay, so in other words, the one that we are supposed to be interested in is not just simply your K space, but essentially the states. Okay, so here we have that differential, where's my cursor, that differential dn to be the volume element k squared sine theta dk d theta d phi multiplied by the density of states. Okay, so this is Lx, Ly, Lz over pi cube. So remember that density. Okay, so given that, now what we want to do next is to simplify this expression in some way by integrating out your angular variables. So let me just put this, push this thing up. So simplify by integrating angular variables and essentially this bounds to this integral. So forget about dk, we just concentrate on the d theta and d phi. So if you want to integrate your theta, it will be from 0 to pi. So this d theta sine theta integral of d phi from 0 to 2 pi. Okay. Remember that the theta angle does not go from 0 to 2 pi, but it's only the z-axis, remember. So what's theta? Theta is going from this point to the z-axis, and then the maximum angle will be this one, which is theta equals to pi. Okay. So otherwise, if you make it to 2 pi because of the other angular variable, then you'll be double counting. Okay. So this, if you integrate, well, we can write it differently now. If I just realize that this is equals to d cos theta, actually it's minus d cos theta, but I flip the angular variables because cos 0 will be 1, so 1 is supposed to be down here, and then cos pi is negative 1, then it's supposed to be up. Okay, but then there is another negative sign from the the differential of cos theta is minus sine theta, so this will be minus of that. Okay, and then you flip the integral limits, and that get rid of the negative sign. So this equals to that. Okay, and essentially this equals to you integrate phi, you get 2 pi, you integrate this, you get 2, so 2 times 2 pi is 4 pi. Okay. So right, now I have to erase this first. Let me do that. So oops, what did I do? Oh, I should use the pen. Give me a minute. Erase this thing off. So let's erase the whole thing off. There's some residue here. Okay. Let's go back here. So, and then the other thing that we should remember is you do not want to integrate over the whole sphere. So if we look back to this picture, it's really the positive outturn. That correspond to the positive k. So that is the thing that we want, because if you do the others, then basically you get multiples of those, which is differ by a minus sign, and the quantum states are not sensitive to this plus or minus sign or a constant factor, so you can ignore all those other octants. So remember, there are 8 octants to complete the sphere. So what do we do? Okay, so to get the positive octant only, you divide by 8. Okay, so so this 4 pi divided by 8 is going to give you pi with 2. So and then okay, and go back to that dn thing. This will give you so let's remember that this is v here. Let me pull this thing a little bit down here. This Lx, Ly, Lz is v. Okay. So that gives us v, and then 2 pi squared, the cube of is gone due to this 4 pi at the top, okay, and then you get pi squared at the bottom. And remember, we have divided this thing by 8, say 4 over 8, that gives a factor of half. And then this is now reduced to only the element that involves your magnitude of your k. Okay, and this is the thing that is being introduced over here, which is what we call dk times dk. Okay, so this is what we call the density of states. Okay, and this works for the case of continuous k. Okay, so this is really the density of states within the interval of k plus dk. Okay, so now one could actually why are we doing this? Essentially, what we wanted to do is to get the partition function. Okay. So usually we think of your partition function is going to be the sum of the exponential of your energy, or the energies, the different energy states, okay, and then divided by 2m, usually by kBt. Okay, so let me just write that down first. So now instead of the sum, okay, we have now conveniently sort of silently move from the discretized k to the continuous k. Okay. 0 infinity dk exponential minus epsilon k on kBt integrate over all possible k. So now this is already taking the fact that we have gone to the continuous k. Why is this possible? No, really, actually, this is already in a sense classical because you're using continuous, but you can also think of this as a approximation that we have taking the small interval within the quantum states, okay, because it's being sort of scaled by your h bar, which is very small. Okay, so and then you turn the sum into an integral that way. But you can now essentially, okay, now I can think of a continuous case just like your classical case. Okay. The real way of doing it is probably much more complicated because of the continuity of your variables. Here we sort of bypass it using some approximation. Okay. So let me get rid of this first. I should clear up the whiteboard folder. Okay. Where were we? So we have done the partition function now. So now what we can try to do is to okay. Right. This is for the case of 3D. So your 3D case is given by what was the density of states here? It's V. So dk here is V on 2 pi squared k squared. Okay. Sometimes what we also need the cases of 1D and 2D because they sometimes appears in some problems. Okay, so let's try to do this. Let's do the 2D case first. Right, I have to clear everything up. Sorry about this. I should clear the whiteboard before this. Right. So let me. Okay. So let's go to the 2D case. There, what one has is your states are really this. The states are given by ny pi over lx x sine n2 pi lx, sorry, ly y. So there is no z component here. So here again, this is your kx. Here's your ky. So they form a two-dimensional k vector. Okay, and because it's two-dimensional, we don't talk about volume, we talk about area. So area of unit cell is given by, instead of pi cube, you have pi squared instead. Pi squared Lx Ly. So that gives us the density to be, density of states to be, sorry, density of points. I should have made that a little bit more clear. Will be Lx Ly divided by pi squared. The density of state is coming from the number of states. Okay, this is the points inside your K space. Right. So again, what one do is to convert your kx ky to polar coordinates, your planar polar coordinates, and do the same thing. So I'm not going to do that again. So I'm just going to write the results. So your dn over here is your density of points, over 2 okay, probably you need to do a bit more work, because here, remember, these are in terms of your Cartesian. When we go to polar coordinates, so you convert your kx ky into a magnitude and a planar polar angle thing, and that when you integrate that, you get 2 pi, and that gives you that thing over here. Okay, let me just write down the result, so we don't have to go this working again in this particular example. What was it? KDK. Okay. So this is now your density of states for the 2D case. So dk equals to Lx Ly can be written as your area here, so A over 2 pi times K. So you can see that it's different here. So let me just draw a square there, okay, and then compare with this. Okay, so here you can see the dependence on your K is a quadratic one. Over here, 2D case, it's only a linear dependence. Okay, and for 1D, I'm just going to write the results. Okay, so let me clear up this thing first. Try to do this a bit more. Oops, what did I do? Let me do again. No, sorry, I have to do that again. Right. So for the 1D case, I'm just going to write the result. The density of states will be given by just simply a constant times dk. That constant is just your length divided by pi times dk. Okay, so depending on the context of the problem, sometimes you have to use all these different forms of your density of states. Okay, so again, this is with respect to density of states with wave number with k vector. So another convenient thing to do is to convert the density of states into with respect to energy. Okay, so let me just probably, I'm going to avoid writing too much now. Again, I have all this thing I want to erase. Then I'm just going to write the results. Okay. So density of states. So this will be with the range of the range of epsilon to epsilon plus d epsilon. Okay, so what do we do in this particular case? We write in this way, d epsilon, okay, and then you have L over pi, oops, Control Z, not sure why that happens, L over pi, and then you use some kind of a chain rule, okay, d epsilon k as a function of k, d epsilon. Okay, so this is the 1D case, 2D case, same thing, but the factor over here will be different. Okay, so this will be a k divided by 2 pi. Again, I'm not sure why this is sort of 2 pi dk d epsilon k d epsilon, again is like chain rule, and finally for the 3D case, so this again, the factor in front will be different. This will now depend on volume and also the k dependence over here, and then here you have 2 pi squared dk d epsilon k d epsilon. Okay, so this will be also convenient because when we discuss about partition function, we are actually referring to the energy states. Okay, so let's try to do an example where one actually write down the energy states. So the energy states over here, we left it as an arbitrary function of k, but for example, in the at least one in the case of the particle in a box case, it's just your kinetic energy. Okay, so your epsilon k free particle, which also applies to the box case, because in the box there is no potential there. So your epsilon k is given by just what? It's p squared on 2m. Okay, and that is actually squared, k squared on 2m. Okay, so then now if we start taking the derivative with respect to k, the epsilon dk now will be just simply h bar squared k over 2m. So now I can sort of plug this into this formula of this density of states. So so let me write down that example. The epsilon of, this is the 3D case, vk squared on 2 pi squared, and then you have the epsilon dk, that gives you, well, we need to take the reciprocal because it's inverted there, so that will gives you 2m, sorry, this is wrong, let me erase that factor of 2 there. So remember, when you take the differentiation, you have another factor of 2 that cancels off that factor of 2. So this will be m over h bar squared k. Okay. You can simplify this to the following. Your k can be written as well as, no, since epsilon k is that, your k squared over here, okay, we can write it in terms of your energy there. So V So let me just cancel that off. Oh, that's all right. 2m epsilon to the half divided by 2 pi squared h bar cube. Okay, where is this 2m epsilon to the half thing is coming from here. K here is k squared here is cancelled off by 1 over its power by k at the bottom there, so your k is the square root of 2m epsilon, okay, from there, divided by h bar squared. Okay, right. So sometimes we need, okay, maybe I should say this. This is sometimes called the way how energy depends on your wave vector, or in this case wave number. It's called a dispersion relation. I'm not sure whether I've done this before, but the idea of dispersion relation is tells you how the probability sort of spreads about a particular peak. Okay, so in the case of so here is essentially your dispersion relation for the non-relativistic case. Now sometimes we do need the case of the relativistic case, and over there, meaning what do I mean by relativistic case? Your velocities are going to be approaching to the speed of light. Okay, so velocity of the gas particles. So in this particular case, your dispersion relation is going to be different. Above is quadratic for the case of the relativistic case, where your velocities are very high, so this becomes a linear dispersion. So again, one can write down your d epsilon there as just write the answer down. Okay, 2 pi squared. I cannot see my own notes. H bar cube. Okay. Right. Okay. Now, how do we connect with the idea of Maxwell distribution of the velocities? Well, again, let's go back to the original idea of Boltzmann. Okay. Boltzmann consider the idea of probabilities. Okay. In this case is PKSA, which is related to your exponential thing. This is for one particle divided by the partition function. Okay. And then we have made some approximation for n particles. Okay. The probability distribution is given by n times pk. Okay, and this only works for low density. That means your n is not going to be giving you high density configuration. Okay, so now what we do is to talk about your velocities over here. So how we're going to do that is through your wave vector. So given, say, density of states, decay, the average number, okay, what we have is now is the probability, right? So now we can do the average number of particles in range k to k plus dk is given by the following. N k bt over z dk. So basically this comes from your Boltzmann distribution, and this is your density of states. Okay, so that is that. And let's recall for free particle, one has worked this thing out before. Your partition function is given by the volume divided by lambda d cube, where lambda d is given by square root of 2 pi h bar squared on mkbt. This is sometimes called the thermal de Broglie wavelength. So what you do is simply to plug those in. Plug those in into your fk dk. So that gives you n lambda d cube over 2 pi squared k squared e minus epsilon k on kbt dk. Okay, so that is simply just your average number of particles. So now let's go to the speed. The speed, you need to write this relationship. Okay, this is really what h bar k, remember, is your momentum divided by the mass, that gives you the velocity, okay, or the speed in this particular case. So you plug this thing into the previous case, then you get the distribution that you need. Because over here you write in terms of dk, then you transform it to du, then you should be able to write this down. So nu du now is given by n lambda d cube m cube over 2 pi squared h bar cube, and then you have the dependence over here, k squared becomes u squared, e minus, well, okay, here I didn't write your epsilon k, so this epsilon k is just your h bar squared k squared. Oops, I wonder why it does that. Okay, so this is your epsilon k. So over here, then it will becomes e minus m u squared on 2 kbt, and then you have the factor, the differential du. Okay, so this is what Boltzmann re-derived. The original derivations made by Boltzmann. So we call it Boltzmann distribution of molecular speeds. Okay, the next thing to do is to, I don't think we have much time left, is to be able to calculate other quantities. Okay, maybe let me just start. So given the all this distribution that we had constructed, then we can start to derive some physical quantities in terms of their averages. Okay? Given distribution Fk, can calculate average value of any quantity. So how do you do this? We're going to prove this later on. This is given by integral of Fk. A will be also function of k, and then integrate over dk divided by integral of Fk dk. So we look into this proof in the next lecture. So I will stop at this particular juncture, and hopefully, how many weeks do we have left before the examination week? Pardon? So okay, here is the thing that because this was really unexpected for us, because we were told there would be no changes to this calendar, despite that we have actually taken leave for about 1.5 weeks. So I'm not sure how to do this, but we need to have some extra lectures, at least to replace those inside your, what you call, the weeks that we have missed. Okay, so I hope you can discuss what free time do you have during. The other thing that can be done, I was told by the head of department, we can also do replacement lectures during night time. I'm not sure whether this is favorable or not, but if there is no possible time during the office hours, then I don't mind doing so. Okay. So can you discuss this during the in the WhatsApp group, so that we can at least say have a replacement lecture of what, 3 hours or something like that. Actually, it should be more. It should be about 5 hours. We miss 1 week, and then another week, which that counts for about 4 hours per week, right? Sorry, 3 hours per week, plus another 3 hours. That was about 6 hours. Okay, so we have to replace those somehow, and I think with that 6 hours, then we could actually finish off until chapter 10. Yeah, until chapter 10. So please discuss how we can do this. I need to discuss also with the other class mine. So if you let me know earlier, then we can fix this particular subject first. Okay. Or the other alternative is to what you call just have recorded lectures. I leave this as the last alternative. So that means I will just upload the lectures without you attending it. So please do discuss, and hopefully now we get to finish all the things that we wanted to do. Oh, by the way, your assignment, you need to hand it in by Wednesday so that I can put out the versions. Okay. So that's it for today. Yeah. Pardon? Yeah, that's the thing that. Okay, that's one possibility. The other thing is, okay, let's discuss this at some other time because I have to prepare another 2 hours of lectures in the afternoon. Okay, so thank you everyone.